So welcome everybody. This is our recording with Professor Dana Picard from Israel. My name is Zoltán Kovács, and it's our pleasure to give you this talk. Unfortunately, we cannot be in presence in Havana, Cuba right now, but we hope you have a good time and you enjoy the conference.
We are so sorry not to be together with all the friends and all the colleagues in Cuba, in Havana, for this. But at least we hope that you will be excited by the mathematics and the technology that we will present you the same way we were excited to discover it. And we are very happy that in this wonderful session of education in ACA, we are every year discovering, exploring, and we are very, very happy to do that.
We prepared some surprising geometrical topic for you. So we hope at least that it is interesting and surprising. For us, it was. It was completely surprising and unexpected. The topic is on Estrella Solitaria. You know, most of you who live in Cuba, but maybe other researchers of the world. The story of this pentagram star, the pentagram formed creature, has a long story. Basically, it was designed in 1849. It's well, kind of history. Yes, so not just the flag of Cuba, but some other nations copied, and many other flags contain this wonderful creature. Well, we will talk about not a straight segment contain the pentagram, but a different creature, different form, and it is an algebraic curve that it is a bit similar to this Estrella Solitaria, the Lone Star flag. The difference is that we have curves at the bordering parts of this. Well, we will introduce a special version of GeoGebra. It is called GeoGebra Discovery. Well, just the first look on the offset curve. This is how it looks like. It contains of three parts. First of all, there is one part here. It's not so interesting, but this part that contains something like the Estrella Solitaria. This is what our focus is today. Well, there is a generator curve. It's quite simple. It's the quartic curve y equals to x to the fourth, and we create the so-called offset curve. If you zoom in to the picture, you can see a more accurate output for this curve. This curve is a polynomial curve, degree of 14, quite high. Well, what is an offset curve? Maybe some of you are familiar with this notion, but maybe other not. So it's a so-called special case of envelope curves, of an envelope curve. Maybe you don't know what is an envelope curve. An envelope curve is, well, there are many definitions. At least 5 definitions exist. One of them is shown here, so-called impredicative definition. There are several books that explain this definition, among others. For example, we mentioned the literature Cox book, or Bruce and Giblin's contributions, Berger. They studied this topic and tried to find a good enough definition. So this is one. If you have a slider here, you can change the position of one curve in the family. This curve in the family is, in this special case, it's a line, but it's not necessary to be a line. It can be a different curve, for example, circle. Later, when we will work with offsets, this will be a circle, but the easiest special case is a line. So what happens if we change the formula for this line? Here you can see the general formula, y equals to 2 times k times x minus k to the square. And in the special case, when k equals to 0.9, then we have this line here, this pink line. But if we change it to different values, then the lines will be completely different. And when we check what kind of curve is a tangent of each of these family of curves, then we get a nice parabola. So you can find a couple of other ways to define envelopes, so-called synthetic definition, or an analytic definition. Here, for us, they are not very useful at the moment because we use implicit curves in GeoGebra to compute not just to visualize, but also to compute the envelope. And therefore, we need to have something like an implicit definition. So for the first, at the first sight, you may think, yes, it's a monster definition. It is. It's quite big, but this is what we are doing. Well, we consider a family of plane curves, and we require for them so-called intermediate construction points. So this family of plane curves require really a lot of steps, or some steps in some cases. And then we define point M, which is a member of the particular curve, which is a member of the family. And also this point is a member of the envelope. So this is how we can define the envelope curve by putting the equations or the polynomials of these equations to an ideal, to a polynomial ideal, and then we create the Jacobian matrix that contains the derivatives of the polynomials with respect to these variables, to each variable. Then finally, if we have the ideal, the polynomial ideal, then we compute the elimination ideal, which means that we consider only those polynomials that contain the coordinate x and the coordinate y. So finally, we hopefully get just one polynomial in x and y. We chose this slide for explaining a kind of strange case when we have the absolute value function as the curve. And you can see that by using circles in that have the center points on the absolute value function, then we have a kind of border for the result. So actually we consider this ray here and this ray here, and then this ray plus this quarter of fourth, I should say a fourth of the circle, an arc, a circle arc, and then another ray in the infinity. So it's quite a complex creature, but this is how we consider the definition of the envelope. Then if we want to get a different definition, then we can do the same by using vectors, namely normal vectors, perpendicular vector. And in such a case, we will usually not get this circular arc, just this ray here, or this ray here, this ray here. So the definition matters. We don't always get the same curve. And also, if we use the circle-based definition, then we usually have a wider set of geometric locus. Some applications, because maybe you you don't know where this offset notion is used in real life. How to define offsets via algebraic geometry? So this is a difficult story, to be honest, because in this case we need to work again with the polynomials, but we add an extra polynomial to describe the circle, which is very important in this definition. Also, we use the Jacobian matrix, and then we have this intersection with q, x, y. So we compute the elimination idea again. Well, you may want to know if it's a simple process or it requires a computational challenge. Yes, it's expensive. So the input degree can be seen here in the second column for some special tests, but you can see that sometimes they are quite slow. For example, if you want to compute the deltoid curves offset, it's well, okay, so you can see it's slow. Not every attempt is successful, and this Cayley oval is not present in the benchmark because we're still working on it. It is the research topic of Daniel Zirkin, a student of Noah's, and he tries to analyze the situation, to study the case here. For the Cayley ovals, at the moment, we don't have an implicit version of this computation, but the other attempts are also very, very difficult. So because of that, we learned if you have a high input degree, you cannot be optimistic if you get a positive result. But then we tried to compute very simple curves. It means that we tried to compute the offset curve and visualize them for such very simple cases, simple in the sense that they are just the monomial terms. So x cubed, x to the fourth, fifth, sixth, and so on. And in such cases, we learned that the timing is well, not very fast for bigger exponents here, but we managed to learn also the output degree, and the visualization was also successful. So we were quite surprised, and well, we also managed to have a conjecture on the output degree. So you can see each time we increase the input degree, we can see that the output degree increases by 4. So that was our conjecture. Well, this is a very exciting moment for a researcher when we learn something new, something unexpected, because we never realized that we can be successful for input degree 5 or 6 or 7. So it was not really possible formerly for any inputs. But for these simple inputs, it was, well, successful. And we had finally a conjecture of the output degree. And then we started to learn something more in the literature. And well, finally, we managed to find a great paper from 1990 from Rida Faruqi. Also, generalization from some years later. Also, we managed to contact another expert, Rafael Stendra from University of Alcalá. There is a nice upper bound for the degree. If you have a degree n algebraic curve and you want to compute the offset curve, at most 2n squared is the upper bound. You can see that the offset curves are here changing when the distance is growing. So this, I will open this file. Now,
well, I hope that the audience will enjoy the animation here, where we can see these curves evolving with the distance of the offset. And it's very, very exciting, and at the beginning, we wanted to call the curves that we discovered by a name that I will not mention, because we discovered after that the name was already taken.
Yes. So if I just move the slider, you can see that everything is computed on the fly, and I can also start the animation. So every curve, every implicit curve that is that appears here is of degree 14, and this is what we have. So this is very close to a star. Well, it's difficult to find a good zoom, because the algorithm, the numerical algorithm in the background cannot really handle this situation of degree 14 curves. So that's why we need a different algorithm if we want to visualize this much better. And as mentioned, so this is how it looks like if we use some more sophisticated algorithm, namely cylindrical algebraic decomposition, to analyze the situation deeper. We need about 8 or 10 minutes to get this curve. So I will not go into the detail right now. Why do we get a curve like Estrella Solitaria? To explain the situation, we need two more notions. So first of all, the oscillating circle and the curvature. So we have a curve and we want to find the best circle that approximates this curve in a given point. If you have a radius of r, then its reciprocal is the curvature. One more idea to explain the situation. So if you have a curve here, it's again very similar to the absolute value function, just a rotated one by 45 degrees. Then if you want to create the offset curve for this this kind of L, letter L, then you will have well, first of all, you have a simple curve on the one side. On the other side, you get a so-called cusp here. So this is what we call cusp. It's quite strange for the first at first sight, but this is what happens. I found this on the Wikipedia. Parallel curves, if you want to check. Hopefully you can get it. Let's study the curvature of this. In this part of the curve, the original curve, we have curvature 0, because if you want the oscillating circle, it has an infinite radius. So the curvature is 0. Here, at this part, the curvature is 0. The same for this part. The curvature is 0. But what happens here? This is a kind of discontinuity, and that's true. So that's the reason that here we have a curvature of infinity, because the radius of the oscillating curve here is it tends to 0. That's why the curvature here is infinite. Well, we can do the same for the other side, where we create here a we mention here a very rough model of the whole story. So if you remember, we had the function y equals to x to the fourth, and this very rough approximation, or this very rough model, tries to explain what happens in this particular case for the quartic function.
It's a well-known theorem that if what is called the progenitor curve. This is the original curve which has been given. If there is a singular point, then this induces generally on the offset a very strange behavior.
In this sense, we can argue that here there should be a cusp in the offset curve, and here again there should be something unusual because the curvature jumps from 0 to infinity, some sense, and here it jumps from infinity back to 0, then it is 0 again, and here it jumps to infinity and then it jumps back to 0. You can see what happens if we get this cusp here and this cusp and we put them together, then we actually get the Estrella Solitaria like pentagram curve. So if you put these two cusps together. Well, you can ask the question why it doesn't appear for a parabola. But in this case, we only have one cusp. So this is one cusp here, or another offset cusp. So we cannot see only one cusp for each distance, or nothing, or no cusp. The difference is in the properties of the curvature. In the first case, if we have a parabola, so this is our curve to be studied, we have the curvature function. This red one is the curvature function, and you can see that there is only one jump here after being approximately 0, then there is a smooth jump until 2, and then there is a smooth jump back. So here we have only one big change in the curvature, and that's why we have only one cusp. On the other hand, if we have the 4th degree, then we have two jumps, like in the case for the 2s. So one jump and back, then one jump and back. And this is what we can see here in this figure. Well, if you want to see some computations, why not? This is done by using computer algebra. Well, it was not completely trivial to compute this, but the curvature computation is quite well known from textbooks. And after simplification and after computing the derivative, we can indeed get that there must be two zeros of this derivative. So there must be two jumps where there is a local maximum. At the case x equals to 0, we have just a local minimum. Yes, and we can exactly compute these numbers where we have a kind of jump. That means that the cusp is around this value. But this works, of course, only if we have at least a quartic. And for some students, we can also give this question, what happens if n is big enough? And we learn that these changes, these jumps in the curvature will be at plus and minus 1. Well, some other figures. So this is for the parabola, this is for the quartic, this is for the sextic, for the octic, and in the case of degree 10, we have again these two jumps. Well, for those who want to try it on their own, it's quite simple to create this. It is very fast. Also in the web version of GeoGebra, you can do that. And if you are interested in the details, how it was computed, well, we used the third definition for the implicit offset curve. One trick that could be interesting for some of you, that we use some linearization steps to avoid to have a large amount of variables. So if we have linear equations, then we get rid of one of the variables and try to use instead the other variables. So we can save variables, but the price is that maybe we get some higher degree polynomials. And finally, we can show how difficult it is to see the final polynomial. So it's not for people who don't like big numbers. Let's comment our results from the point of view of a teacher. People or students usually don't know how researchers look like. What we are doing is actually research, even if it's not research like, yes, we only have paper and pencil and that's all. Research is exploration. And this is what we would like to communicate today to you and share our thoughts on this. Just one interesting part of our local story in Austria, there is a so-called Lange nach der Forschung, which means that young people go to universities, university colleges, companies, and they explore things. Let's summarize some very interesting ideas how we face this research project. Well, we tried to generalize something by using the Cayley oval, and we didn't manage to do that. It was a failure. Then we tried to specialize this generalization, and it was unexpectedly successful. Then we tried to generalize this in a different direction by using only monomials, and it was again a success. So we were happy with that, and then we tried to name this curve. Well, then after studying the literature and contacting other experts, we tried to work hard on the tools to get even more beautiful results. It's a work in progress, and then we tried to work hard on proving the results, and it was, in some sense, again, successful. Another important thing is that we use computer algebra quite widely, and not just computer algebra, but also dynamic geometry. The combination of these two is unavoidable. And two last things, some classic concepts from the differential geometry, like curvature, oscillating circle, were us also kind of new chapter of in our research. And for our students, we learned again that proving with the help or without the help of computer algebra is very, very important. Thank you very much for your kind attention. So thank you again, and we wish you a wonderful conference in Havana.
Thank you very much.